Assalamualaikum dan selamat sejahtera. My name is Muhammad Faris Minuddin. My matric number DE180191Y. My supervisor is Dr. Mat Zarafi bin Ahmad. And my panel is, first is Dr. Siti Mali and the second panel is Dr. Kok. So today I will presenting my final project which titled Winding Slot Improvement Analysis of Radial Field Excitation Coil Flux Motor for Optimal Performance. For introduction, HFSM is upgrade from the PE FSM, which is Permanent Magnet Flux Switching Motor, and also upgrade from the PE FSM, which is Field Excitation Flux Switching Motor. So from the upgrade, produce the HFSM, which is Hybrid Excitation Flux Switching Motor, is combination flux produced from the permanent magnet and field excitation coil located on the stator to create a further excitation flux. So the operation of the HFSM is exchanging the polarity of the FEC flux linking with the armature coil flux to the rotor position. So the benefit from the HPSM motor is to we can get to improve maximum torque, power, and motor efficiency. So the problem statement, by referring the right figure, which is this figure from the previous study. This is for the armature, this is for the AVC. So from this figure, we can see the problem. There is an overlap winding between armature and radial AVC winding. So from the overlap winding will cause the high coil end to have higher losses, high flux saturation in the flux distribution, and also decrease motor efficiency. So to prevent the overlap winding, AVC slot and armature coil slot need to be improved. So the objectives of this project is first to improve the flux distribution of armature and field excitation winding slot of HFSM. Second is to examine the optimal of the motor performance in terms of cogging torque, BMF, flux leakage, flux distribution, and also output torque of HFSM. So this is for the scope. The specification of the motor is based on the table 1. So the outer stator outside diameter is 134.5 mm and the radius of rotor is 97.25 mm with a rotor angle 12.8571 degree and the stator angle is 15 degree. So the permanent magnet weight is 1 kilogram. So the second scope is the analyzed performance divided by 2, which is no load and the load analysis. For no load, will be analyzed in terms of cogging torque, BMF, flux leakage, and the last one is flux distribution. For load condition, the JE at various JA need to be analyzed by using the JMAT designer as a finite element solver. The rated restriction of the electrical of maximum 650 volt DC bus voltage and maximum current is 330 ampere. So the armature current JA and the FEC current density JE is fixed at 30 ampere. Okay, this is for the part methodology. Basically, this figure shows the general flowchart of FIP1 and FIP2. So in FIP1, we need to design the motor to a slot at 14 poles. In the FIP2 is the improvement of the motor from the FIP1. So basically, we use the geometry editor to design the motor to a slot and 14 poles HFSM. If the design have overlapped design, we need to change the parameter. If not, we need to move GMAT designer to setting the materials condition, and after that, we need to proceed to no load analysis and load analysis. Okay, then we proceed to the FIP2. So basically in FIP2 we need to modify the motor, which is we need to change the AC parameter, which is armature coil. If the AC slot area not in around 168.40 mm square, we need to change the parameter of the AC parameter. If the slot area around the 168.40 mm square, we need to proceed to change the parameter of FEC, which is R5 and R6. After that, we proceed to the no load analysis, which is cogging torque, back EMF, flux leakage, and flux distribution. If the cogging torque not less than 9.6, we need to change the parameter until the Gaussian torque decrease below than 9.6. If yes, we proceed to the load analysis. So this part is how to design the motor of 12 slot 14 pole of HFSM design. First, we use the geometry editor to design the rotor, setter, permanent magnet, and slot FEC. And last one is armature coil. If from the design there is an overlap design, we need to change the parameter. And then if there is no overlap design, we need to proceed the GMAT designer, which is we need to set the materials, condition, circuit, and also the last set the mesh and study. If success, we need to proceed to coil test. If not, we need to change the setting. If yes, we need to proceed the coil test analysis, and then we proceed to the zero rotor position. And after that, we need to uh, uh, find the U phase, and also U phase must be in 90 degree until 270 degree. If the U phase not in the range, we need to change the rotor position again. And after that, if yes, we need to proceed the three phase arrangement. So this is for the flowchart of armature coil and efficiency improve of the HFSM design. So basically, the armature coil we need to modify the slot area, which is slot area must be around 168.40 millimeter square. If not, we need to change the parameter. If yes, we need to proceed the ABC modification of R5 and R6. Then we proceed to the Gaussian torque analysis. The Gaussian torque analysis, if the Gaussian torque more than 9.6, we need to change the parameter of ABC, which is including the R5 and R6, until the Gaussian torque less than 9.6. If yes, we need to proceed to the no load test, which is back EMF, plug leakage, and the last one is flood distribution. And after that, we need to proceed the load analysis, which is the analyze the output torque analysis. So this is for the complete design of 12 slot and 15 poles of HVSM. Figure 2 is the conventional design. Figure 3 and 4 is the improvement design from the conventional design. So in figure 2, the specification as I mentioned at the objective, which is the table 1 for the specification. And for the figure 3, I changed the armature shape with 168.40 millimeter square, and the FAC slot area with 230.55, same with the conventional design. While in figure 4, I changed the AC shape with 168.40 millimeter square, and the FAC slot area with 184.36 millimeter square. This improvement from the initial design. So this is for the final design. By improving the 12 slot of 14 pole of HVSM. So you can see this is for the armature, this is for the AVC. So the parameter that I changed from the conventional design and to the final value. So we refer to FEC first. From the FEC, I changed the R6 and R5, which is FEC width and FEC height, which is for the conventional design is 676, and the final value is 6.39, and the height is 29.98, and the final value is 28.78. So we move to the armature coil. I changed the parameter of R7 and R8, which is from the conventional design, the amateur wide is 6.46 and the final value is 9.434, and the length of the amateur is 26.006 and the final value is 17.85, and the slot area in range 168 and 167, and also both of the final value and the conventional value, the number of turn of the amateur coil is 7, and then for the number of turn of FEC reduced from the 57 to 46, which means this area, the final area is much decreased from the conventional design. So this is for the flowchart of coil test. First, we need to do 12 coil test. Second is 3 group coil test, UVW coil test, 100, and if the design shift 120, we need to proceed the next step. If now, we need to change the arrangement. So basically, this is for the result for the 12 coil test and 3 group coil test, which is 1 until 12, and this is group, which is group U, group V, and group W. So group U must, as I mentioned at the flowchart, design the motor, you first need to in 90 degree until 270 degree. So this is the result for the 12 coil test analysis. So figure 6 is graph of V flux, figure 7 is graph of W flux, and the last one, figure 8, is the graph of U flux. So in the 12 coil test analysis, the magnetic flux will be generated by the permanent magnet as the source for the flux and obtained by each of the amateur and FEC coil. So for the graph of U flux, I already rearranged the rotor position will be adjusted at the negative 2.2 degree to obtain the intercept between 90 degree to 270 degree. So this is for the result 3 coil test analysis. So basically, in this part, we combine the UVW phase into the one graph, which is in this process we need to convert the single phase to the 3 phase. So the maximum amplitude from the graph is 0.01243 Weber. So this is for the result for the no load test analysis of the cogging torque, and the figure 10 is the graph of cogging torque between design, which is conventional, initial, and final design. So basically, the cogging torque occur when there is an air gap in between machine, which is a gap between stator and rotor. So from the analysis, the final design produce 8.3 torque peak to peak, has produced lower cogging torque compared to conventional design, which is 9.6, and the initial design is 20.6. So this is for the no load test of the back EMF. So by referring the graph 11, which is graph of back EMF between design. So the BMF is the voltage generated in electric motor when there is relative motion between the stator winding and the rotor magnetic field. So from the graph, the final design show the lower back EMF, which is 22.426 volt, compared than initial design, which is 42.576 volt, and the conventional design is 54.921 volt. So what I can say here, the BMF for the conventional and initial design has distortion that can give effect on lower torque and reduce the motor efficiency or motor performance. So for the final design, is more sinusoidal waveform, which means less distortion, can provide good in practical application. Next is no load test analysis of the flood leakage. So from the figure 12 show the graph of the flood leakage between design conventional, initial and the final design. From the flood leakage, the flood wave generated from the permanent magnet. The flood leakage of the final design has slightly lower flood with 0.0032 Weber compared than initial design of 0.0062 Weber and conventional design of 0.00849 Weber. Next, we move to the no load test analysis for the flood line analysis. So basically, figure 2 is the conventional design, figure 14 is the initial design, and figure 15 is the final design. So, in the flood line analysis, the flood path generated from the permanent magnet, and most of the flux flow around the stator and the LVC. So, the high flux flow into the rotor cause the high gap density, and this condition will be occur flood leakage and flood cancellation. So from the analysis, from the conventional design and initial design produce more flood flow through at the fourth rotor poles. Here you can see, or you can see at the first rotor poles. You can see here, causing high generate back EMF compared to the final design, which is the reduced flux flow at the fourth rotor, and the result lower back EMF. So next is the no load test of the flood distribution analysis. So figure 16 is conventional design, 17 in initial design, and the last one in 18 the final design. Okay, from the slot between permanent magnet, FEC, and amateur coil slot have a limit space and effect on the flood saturation in stator part and FEC part. From the figure 16, the magnetic flood density at the maximum load is 1.8932. Beyond this value, the flood starts saturate, which can be seen at the armature, and the outer stator in the red circle. You can see here the red one is the flood saturation happen. Okay, we move to the figure 17. The flood distribution in the initial design is obtained maximum is 2.0149, and the minimum of the magnetic flood density is 4.7835 times of -0.005, which is the flood density is better than the maximum of conventional design, which is 1.8923, and the initial design is 2.0057. So as I mentioned before, beyond this value, the maximum value, which is conventional, initial, and the final design, beyond this value, the flood will start saturate, which can be seen at the armature and APC of the outer stator and the red skull. You can see here, and we can see here the initial and the final design. We can see the less flood saturation, which is which is less red saturation. We can see here from the saturation from the red one, and we can see the between armature and the AVC, the flood saturation happen here, and also same the final design. Okay, next we move part load test analysis, which is we need to analyze the top performance of the FEC density JE at various armature current density JA. So basically figure 19 show the result of the average of the output torque versus JE at various JA is equal to 30 ampere. So from the analysis, when the JA is set between 5 until 10, the output torque will decrease at the JE at 20 ampere. You can see here the output torque will decrease. So next is when the JA is set between 15, the output torque will maintain the constant for the for JE greater than 25. You can see the output torque is maintained. And for the JA at 25 and JA at 30, the maximum output torque is obtained for the 25 ampere is 279.48 torque, and the JA30 is equal to 292.05 torque. Okay, from the graph, it is also clear for the JE of the JE of 30 ampere, very much flux of the FEC is generated and the torque is increased. It shows that the less magnetic saturation or flux cancellation happen. So this is for the load test. Same graph before, just this graph for the graph output torque between design, which is conventional, initial and final design. Okay, for the final design, the maximum output torque is 295.258 torque, which is higher than the initial and final design, which is initial is reached 273.509 and the final design is 292.047 torque. Okay, the last part is part conclusion. First is the main objective has been achieved as in terms of improving the cogging torque, BMF, flood leakage, flood distribution of the 12 slot and 14 poles of HFSM performance. Okay, from the final design, by changing the perimeter of armature and with the slot area around 168.40 millimeter square and decreasing FEC design slot area from 230.55 millimeter square of the conventional design to 184.36 of the final design was proved can reduce the number of FEC turns from 57 to 46 turns. Also can reduce the cogging torque, which is 83 torque, reduce the flood leakage, which is 0.00329 Weber, and also reduce the back EMF of 22.426 volt for the silent rotor of the 12 slot 15 poles of HFSM. Okay, however, the output torque of the final design obtained 292 of 4047 torque was lower than the conventional design, which is 295.258 torque. Okay, for part recommendation, I have two points here, which is we can improve for the next future study. We can improve the slot area of the armature slot to reduce the number of armature coil turns to improve the cogging torque and also to improve the output torque. The second is change the FEC corner design to the circle design to reduce the stress and flood cancellation between in the FEC shape. So that's all from me. Thank you.